So, on to Unit 12. Today's 12.1, predicting and explaining how different properties of gases will change when another property is changed. And so let's go through the different variables of the ideal gas law. So we have volume represented with a V, which is the amount of space occupied by the gas, the volume of a container, all that. This is measured in liters, but a lot of times it'll be given in milliliters. So just a reminder that in 1 liter, there's 1,000 milliliters. Amount of a gas is measured in moles and is represented with a lowercase n. And a lot of times they're going to be given in grams. And so to convert between them, there's a lot of periodic table conversions that you're doing with dimensional analysis and stoichiometry. Pressure, represented with an uppercase P, is a measure of the amount of the collisions of particles with the container and with each other. So how many times the molecules are running into each other. Measured in atmospheres, and there's going to be a lot of conversions that we're doing here. So 1 atmosphere is equal to 760 millimeters mercury, 760 torr, and 101.375 kPa. And these three conversions are provided to you because that's a lot to memorize. But just remember that you're getting 2 atm. Temperature represented with a T in the equation. So we all know temperature is hot and cold, but just a reminder that that's a measure of the kinetic energy in the system, the speed of the molecules. So more speed means higher temp, low speed is lower temp. So we're measuring this in Kelvin instead of Celsius or Fahrenheit. And so to get to Kelvin, you can take whatever degrees in Celsius and just add 273. And so if it's 0 degrees Celsius, it's going to be 273 Kelvin. If it's 2 degrees Celsius, 275. So you're always adding 273. It's never a different number. And why are we using Kelvin? Since temperature is a measure of kinetic energy, you can't have like negative kinetic energy. Then the lowest you could possibly get would be 0 Kelvin, absolute 0. But we haven't gotten there yet. And so Kelvin's just better than degrees Celsius. Just a reminder, direct relationship means that the trend is going the same way. Two things are increasing or two things are decreasing, and they're on opposite sides of the equation, which I'll show you in a moment. Inverse relationships is the other way around. One goes up, one goes down, and they're on the same side of the equation. So here's an example. The volume of a gas decreases in a rigid sealed container, which means the volume and the volume's changing, but the temperature's remaining constant, and everything else is constant except whatever it's like saying. So what'll happen to the pressure? So less volume means that there's going to be more collisions because you have the same amount of particles in less space. Remember, pressure is the amount of collisions, so higher amount of collisions means higher pressure. And these are going in opposite directions, and therefore it is an inverse relationship. And again, that little hack is really necessary. PV equals nRT is the ideal gas law, and pressure and volume are on the same side, and they're inversely related. So just a little reminder that that equation can be really helpful if you're not sure which way it's supposed to go. If the number of particles of a gas increases in a rigid sealed container with constant temperature, what'll happen to the pressure? So increasing the amount of particles, it's going to make for more collisions, which again literally means that that's more pressure. which is a direct relationship because they're both going up. If the temperature of a gas is increased in a rigid sealed container at a constant volume, what will happen to the pressure? So increased temp is increasing the kinetic energy. So it's increasing the speed, going faster. They're going to collide more, which means that's a higher pressure. And that's a direct relationship. Again, PV equals nRT. Pressure and temp are on opposite sides of the equation, and it's direct. So just, again, if you're stuck, always go to the equation. If the number of particles of a gas is increased in a sealed, flexible, container is flexible this time because the volume is going to change, what will happen to the volume? So more particles is going to make them collide more. And so they're going to try and expand the amount of space that they're filling up because they're colliding a bunch. And so they're trying to get away from each other. And so that means that the volume is going to go up, which is a direct relationship.